happen is that if I think of t, and I think of sigma 1 of t, then let's see, I'm looking at the origin, so the origin is maximum. What happens is from the left, I can say one eigenfunction which achieves the max. When I increase t positively, some other one becomes better. Okay, so I get that kind of picture. So typically, multiplicity, I get a Lipschitz picture, which is not smooth. It's not C1. Okay, and so but what I can do, so I can't argue that that the Euler-Lagrange. So if the Euler-Lagrange equation would hold, it would say that this is 0 for all h, and so then we could prove something which is not possible really. But so what we can prove from we can look at left-hand derivatives and right-hand derivatives, and what we can prove is that this quadratic expression. So this is a quadratic expression in U. What we can prove, I just reverse the sign here. We call it QH of U. And so, given an h, we get a quadratic function on the eigenspace at 0, at time 0. And the statement is that quadratic expression is indefinite. It's an indefinite quadratic form. In other words, it has some negative and some positive values. And so the reason for that is when you approach from the left, you get one sign, and when you approach from the right, you get the other sign. So that's the conclusion you can draw from the maximization. And so then what you do is you interpret this condition in terms of convexity, the convexity condition. So you consider the convex hull of the pairs tau of u squared. So those are the functions of u that appear in the formula, and where you consider first eigenfunctions u. So actually, the first eigenfunctions, of course, form a finite dimensional space, and also these pairs lie in finite dimensional space because they're quadratic functions. So if I choose a basis for the eigenfunctions, then I can write a basis for the quadratic functions. So I'm going to think of this as this is lying in it's a convex subset of a lying in a finite dimensional subspace of the Hilbert space. So the Hilbert space consists of symmetric 0-2 tensors inside and functions on the boundary. And so you use the step 2 result to argue that you cannot separate that the origin, or the vector 0, 1 lies in the convex hull of these pairs. So that's the point. See, if it didn't, then you could separate it from. You can find a linear function which separates, and the fact that I put 1 in the second slot gives you the integral condition of the boundary. So it would tell you that there's some h for which the QH of u is positive for all u. Whereas step 2 said that for any h, there's always a u for which it's 0. And so that's the idea. And so once we have 0, 1 lying in the convex hull, since it's in a finite dimensional space, I can actually write it as a finite convex combination. So I can find positive numbers and eigenfunctions so that the sum of squares ai squared tau ui 0, and this is 1 on the boundary. And then I can take my map to be this. And then if they happen to be dependent, I can just successively reduce I can reduce the dimension to make them linearly. Okay, so that's a rather interesting argument itself. Okay, so in particular, it tells us that if we can actually maximize with a smooth metric, then we can realize the maximum by a minimal surface reduced metric. Okay, so let me come back to these minimal surfaces again and give you more examples and information about this. So remember the class of surfaces we're looking at are submanifolds. We can look at proper submanifolds of the ball, and we assume they meet the boundary orthogonal. Those are the class of surfaces. And the coordinate functions that are harmonic inside, and they satisfy the condition that the Steklov eigenfunction condition eigenvalue 1. And so there's a picture. So for a submanifold, h equals 0 inside is exactly equivalent to the statement that the coordinate functions are harmonic, and the orthogonality of the boundary is exactly equivalent to the Okay, so let me give a class of examples of these. So the first basic example, of course, would be just a flat disk, K-disk, through the origin. So obviously that means the boundary orthogonally. And as I said, indicated in my lecture on Monday, there's an older theorem in Nietzsche which says that in fact these are the only simply connected solutions of B3. And in fact, recently we actually extended that to Bn. So in fact there aren't any non-trivial three-boundary disks in Bn. However, if we go to an annulus, which is the next simplest topology, then there's a sort of obvious one, which is called the critical catenoid. So the catenoid is the surface of revolution gotten by revolving a hyperbolic cosine curve. So I can then look at a line through the origin that's tangent in the first quadrant, and then I can draw a circle, that radius meets perpendicularly, and then I can revolve about the axis. Okay, so there's a sort of unique sphere for which the catenoid is a three-boundary solution, and then I can just scale the ball to unit size, and I get what's called the critical catenoid. Okay, so in particular, that's a solution with genus 0 and two boundary components. In fact, that's actually the only solution we know with two boundary components at all. And actually, the disk is the only solution we know with one boundary component for three boundary solutions. However, if we allow three boundary components, then there should be infinitely many such surfaces. And in fact, some people are working on doing this rigorously. But it should be true that if you allow three boundary components, there's a very natural picture of an infinite family of surfaces with genus going to infinity. So you get the picture by just taking the union of the catenoid, so there's one cross section. So that's supposed to be the critical catenoid and the disk to the origin. Okay, so this, when I take the union of those two surfaces, I get an immersed surface. So there's a circle of self-intersection. There's a circle self-intersection of the two surfaces, and then the idea is to regularize that by putting in handles. And in fact, there are rigorous theorems that do that under certain settings. Not exactly in this free boundary setting, but presumably those arguments will work. And what that would do is it would construct surfaces with three boundary components, free boundary surfaces with arbitrarily ideas. And there are a lot of conjectures about non-existence or existence of surfaces with one or two boundary components, but there isn't much known beyond the use cases as far as I know. Let me mention one more example which is important for us for our eigenvalue problem. That's called the critical Mobius band. Okay, so we really found this kind of from an eigenvalue consideration, interpretation. I don't know whether this minimal surface exists in the literature or not, but it's quite easy to construct. So we think of the Mobius band as R cross S1, where we identify T theta with minus T theta plus phi. And then there's a rather natural minimal embedding again in R4, which you can write down in separated form. So I'm just taking the product metric on R cross S1. So that a function like this, sinh T cosine theta, is a harmonic function. Product, right? So it's harmonic. And so it turns out if you write down, this is sort of the simplest such math. So you write down 2 sinh T cos theta, sinh T sine theta, and then cosh 2T cosine 2 theta, cosh 2T sine 2 theta. So this phi is invariant under the identification. So if I replace T by minus T and add pi to theta, then these first two functions are both odd, so they're invariant, and the second two functions are both even. And so this is well defined on the Mobius band. It turns out to be an embedding, and you can check that it's minimal. So it's harmonic, and you have to check its conformal. So that's just an easy calculation to check that. And that's the reason for the constants there. And so we have this natural proper embedding of the Mobius band into R4 as a minimal. It's a manifold, and then we can look at intersections with balls, just like we did for the annulus case. Okay, so it turns out, it's not so hard to see, that there's a unique interval, symmetric interval minus T naught across S1, where when you intersect with the ball of corresponding radius, so the boundary goes to a sphere. When you intersect with that radius, it meets orthogonally, so you get a free boundary solution for the angles. In fact, you can explicitly compute well, more or less explicitly. It's a unique positive solution of this transcendental equation. Okay, and so we'll call that the critical Mobius theorem. Okay, and so again, there's a theory that parallels the theory for closed surfaces. So first of all, there are coarse upper bounds. These are the analogs of the Yang-Yao upper bounds. In fact, the proofs are quite similar. Particularly the second one is very similar. The first one's a little different because it comes from considering conformal branch coverings which are proper from the surface of the disk, the so-called Alford's functions, which we actually did in our first paper. We gave that upper bound. And this other upper bound follows by just compactifying the surface. So you can take your surface and fill in the disks and extend the metric, and then you can just think of it as you can do your averaging over the corresponding arc length measure, and in fact you get an upper bound. This is in fact exactly the same upper bound as the Yang and Yao upper bound. It depends only on the genus. So for large K, this one is better. For small K, this one is sometimes better. So the constant is small. And actually, neither of these. I mean, we really don't know whether these are sharp in general. But if in the genus 0 case, we can show. In fact, we showed in our first paper that this is definitely not sharp. This is not a sharp bound. Okay, and so however, it's sharp in just again 0 case. This is the Weinstein case. Okay, and so the question we want to ask is, what's the sharp constant for annuli or surfaces? Okay, and so let me now state the main theorems that we've been able to prove. So we've been able to give pretty good understanding in the genus 0 case. The higher genus case is still spurious, but so the first result shows so the answer for the annulus, of course, is going to be the critical cat length. That's why I introduced it, and so the first theorem, you have your theorem A, actually characterizes the critical cat length in terms of, it gives an eigenfunction characterization. So it says that if I have any free boundary minimal annulus in Dn, and if I assume that the coordinate functions, so remember the coordinate functions are always then Steklov eigenfunctions with eigenvalue 1. If we assume that the first Steklov eigenfunctions, then the result is that the surface is in fact a critical cat length. In fact, it lies in the three-dimensional ball. So that's the first theorem. And then there's a corresponding uniqueness theorem for the critical Mobius band. So if I have any free boundary minimal Mobius band in Dn, such that the coordinate functions are first eigenfunctions, then we're actually in 4 dimensions, and it's the critical Mobius band. Okay, so in particular, it does give a characterization of the critical catenoid, but it requires knowing that the coordinate functions are first eigenfunctions. So in general, there could be other. I mean, it doesn't say that there are no other free boundary internal animal. Okay, and so those are two. So the first theorems are uniqueness theorems. So the only cases in which we're going to be able to explicitly identify the surface that maximizes are these two cases. Well, the disk and of course those we know, and the annulus and the Mobius. The other results are more a little more rough. They sharp bounds. So then what we can do, let's take oriented surfaces with genus gamma with the boundary component. Then if we call sigma star the supremum, sigma 1L over smooth metrics, then we know that that's a finite number, and we want to show that it's achieved. Then Weinstock's theorem says sigma star 0, 1 is 2 pi, achieved by the disk uniquely. And then for 0, 2, this theorem says that the maximum is achieved uniquely by the critical catenoid. And you can calculate the number, you can approximate the number. It's about 4 pi over 1.2. So it's bigger than the disk, but less than 4 pi. So that's theorem 1. And theorem 2 is a statement about surfaces of genus 0 with any number of boundary components. Okay, so it turns out if we look at sigma star 0k, it's not very hard to show it's increasing with k, but in fact it's strictly increasing, and it converges to 4 pi. So the result is that when I take genus 0 and I add lots of boundary components, the upper bound of sigma 1 times L is always less than 4 pi, but it converges to 4 pi as k tends to infinity. And so for each k, there's a maximizing metric, and it's achieved on a free boundary minimal surface in D3. And its area is less than 2 pi. So the limit of the surfaces as k tends to infinity is a double disk. And for large k, so it's approximately a parallel plane. So this is the left-hand thing is there, my hand-drawn rough sketch. So it's a little hard to see because the disks are supposed to be filled in here. So you're supposed to think of two parallel disks very close together, and you bridge them at the boundary. So you put around the boundary k little bridges joining the top to the bottom disk. This is a computer-drawn picture, which maybe a little better. I don't know, but it's I don't think the shape is quite right. So you can see an upper disk and there's a lower disk down hidden there, and then there are the bridges. So the boundary components are these little short circles here, little curves. So there are a whole bunch of little curves. And so in this picture, the boundary component would be this one. It goes between two neighboring bridges. Okay, and so the claim is that the extremal surface looks roughly like this. We don't know exactly what it looks like. We don't have a way of really computing it. So in particular, as a corollary, it shows that for every k, that is any number of boundary components between 0, there is an embedded free boundary minimal surface in D3 with that topology. And moreover, it's embedded by first eigenfunctions, that is the coordinate functions. So roughly speaking, you can understand the shape of the neck by a kind of asymptotic blow-up argument. So each of the necks, if you take k very large and you scale it up to unit size, it will converge to a half catenoid. So you can think of the catenoids. Think of the catenoid as a very small hole, very small neck. That. And then cut it in half this way. Okay, so there's an upper plane and a lower plane. So you can think of the catenoid as what you get by taking two planes very close together and putting in a bridge, a neck joining them. Now, if you cut that in half vertically, then you'll get a pair of half planes joined by a half foot little bridge. Okay, and that's what these look like. So you can actually rigorously argue that if you do a blow up of any one of these necks, that is, you let k tend to infinity normalize in the curvature of 1, you can argue that the limiting configuration is net that. So you can understand pretty well what the surfaces look like. And in particular, it gives asymptotically a sharp upper bound for the surfaces, for the signal. Okay. So let me just say what goes into this. And again, there's a sort of difficult existence there to start with. So I don't know how to do this from scratch without knowing the existence of a maximizer. So the first step is to show that for any k greater than or equal to 1, if you take a surface of genus 0, k boundary component, then there exists a smooth metric of maximizers. And actually, you can take that metric to be, in fact, smooth and non-singular. It doesn't have any contours. You can take it to be a smooth metric. Okay, and so again, if I have time at the end, I may talk more about this business, because I think the method we developed is a much more effective method, which actually recently a young French mathematician has used that similar method for compact surfaces to reprove that version of this thing. So it's a much cleaner proof of the existence. I probably have time to talk a little bit at the end. So very roughly, there are two parts to the proof. One is, so generally when you're trying to prove convergence of metrics on a surface, there are two issues. One is whether or not the conformal structure converges. Right? So any metric induces a complex structure, a conformal structure. So you can first ask whether that converges, and whether that's bounded in the moduli space conformal structures. And then secondly, once you have that bounded, then you have to understand whether the metric itself. So you can then write it as a function times a nice metric, and then you have to argue that the conformal part is also controlled. So there are two parts to be proven. And so let me just show how the existence theorem implies theorem 1. Yeah, theorem 1 is the result to the critical. So, okay, so that's the existence, and so the way it works then, this is the restatement of theorem 1, is you first assert the existence of the metric on the annulus, then we use that theorem we proved earlier that if you have a maximizing metric, then it arises from a free boundary minimal surface of the ball, and then you use the uniqueness statement. First get the existence, and then the maximizing metric gives us a free boundary minimal annulus, and then the uniqueness result that we have shows that that is in fact the critical cavity. So that's the argument. And somehow, I didn't state the theorem, but there's a similar theorem for the Mobius band. Okay, let me say a little bit about the limiting arguments k tends to infinity. Okay, so it's really based on a simple geometric property of the surfaces you get, which follows from results about nodal sets of eigenfunctions. And so the key thing about genus 0 is that, so there are several things that one can prove. So actually the theorems, the multiplicity theorems and such, which are well known for compact surfaces, actually extend also to the Steckhofer case. So you can, in particular, you can prove that the multiplicity, so if you take genus 0, you can prove the multiplicity of, for any k, the multiplicity of sigma 1 is the most 3. So there's an upper multiplicity bound, which is 3. So that's why you can assume that you're in B3 to begin with, because the coordinate functions are first eigenfunctions. So the dimension n has to be less than or equal to the multiplicity of independent eigenfunctions. Okay, and so that's one basic fact. There's another basic fact which again follows from the same kinds of considerations, follows from the Courant noble domain theorem and topological considerations. And that is that if I take any first eigenfunction, a non-zero first eigenfunction, then if I'm on the noble set, if u of x equals 0, for x in the interior, x in m, then the negative u of x is non-zero. So in other words, the nodal sets are actually smooth curves. There are no critical points on the nodal curves because of the genus 0 assumption. Again, it follows from the Courant noble domain. If you had a critical point, then you would have locally multiple regions, and you could argue because of genus 0 that you produce more than two nodal domains, which violates the Courant noble domain. Okay, so those are the key geometric things that are used, and so the way that's interpreted. So now if we take our free boundary minimal surface in B3 now. So the first eigenfunction, we get first eigenfunctions by taking planes through the origin, that is the 0 sets or planes through the origin. So if I take any plane through the origin, take a plane passing through the origin, then that is the 0 set of a linear function. The linear functions are first eigenfunctions, and so what you conclude is that every plane through the origin intersects the surface transversely at all interior points. So what you can argue from that is that the surface is embedded and star-shaped. So in fact, from that property, you can get that it's locally star-shaped. You can get that at any point on the surface, if I take a point on the surface, then the normal vector, so this is my surface, sigma, then the normal vector can never be perpendicular to the ray. This can't happen, because if that happened, then then the ray through the origin would lie in the tangent space, and so I could take the tangent space as my linear function, as a zero-7 linear function, and that is not transversal. Okay? So in other words, the interpretation of this notable conditional property tells us that the surface is locally star-shaped. In other words, it tells us that if we take the position vector, x, we take the support function, x dot nu, it's a positive everywhere. Yeah. Either positive or negative, so we can change the normal to make it positive. Okay, and so that tells us that locally the surface is a graph over the sphere, and then you can make an argument sort of filling in the boundary curves using the boundary condition and sort of covering space argument to argue that in fact it's globally a graph over the sphere. So if I take the projection, so first of all the origin doesn't lie on the surface, and then if I take the projection x over mod x, I actually get a diffeomorphism onto the domain of the sphere. So let me just go back to the pictures and you can see that that's reasonable. So if we take the critical catenoid, you can see that, of course, it does have the property that it's star-shaped. It's a graph. It's a radial graph. And similarly, these surfaces all have that property. So think of the origin there. If I took the x over mod x and I just project to the surface, what I would get is the sphere minus a whole bunch of little circles removed on the equator. And so it's really that's a very key geometric property which enables us to understand the limit of these things. What we're going to try to do is understand the limit as taken into infinity. Okay, and the other good thing we have going for us is we have the coarse upper bound. So the coarse upper bound tells us that in fact we have an upper bound which is independent of k. So in particular that implies that the areas are uniformly bounded. In fact, if you plug in the coarse upper bound, you get the area is bounded by 4 pi. So let me explain that. So the coarse upper bound. So here we're assuming sigma 1 is 1, right? So the coarse upper bound is telling us sigma 1 times L is bounded by a constant. I think that constant is 8 pi. That's the coarse upper bound. And so since sigma 1 is 1, that tells us that L has an upper bound. On the other hand, for free boundary minimal surfaces, it's not hard to see that it's always true that the length of the boundary is 2 times the area, or generally k times the area. K is the dimension. So that follows just from using the fact that the divergence of the position vector on a minimal surface is the dimension, and then using the divergence there. So this is true for any free boundary. Okay. So in particular, that's telling us the area is bounded by 4 pi. So the coarse upper bound gives us an upper bounded area, so we're in pretty good shape. We have these surfaces with bounded area. Now the fact that they're star-shaped is very good from the minimal surface point of view because it implies the surfaces are stable. They're stable critical points of the area. And then for stable surfaces, especially with an area bound, we have good compactness theorems. We can prove the curvature is uniformly bounded. And so in the interior, we can take a limit. So we can take a limit of these surfaces where we first take a subsequence, and we can take a limit, and we produce a surface which is smooth in the interior. It might have multiplicity in general, but it's nonetheless a smooth surface in the interior with multiplicity. Okay, and so there's a slightly tricky point to show that the surface in fact must have multiplicity. So the surface has to be, because it's singular, becoming singular near the boundary, you can argue that in fact you get a surface with multiplicity. And moreover, the star-shaped condition implies the multiplicity is 2 at most, because you see these surfaces don't, if I had higher multiplicity, they're converging to the interior. If I had, say, 3 sheets locally, then on one, I could always find a ray which intersects the surface twice. And so I have to be in a situation where the multiplicity is exactly 2. And then you can argue that the limit actually contains the origin, and then you can prove it's a flat disk. So you can prove that you have a multiplicity 2 flat disk with a limit. And then there's another point to show that generally the convergence is very complicated in the boundary, so you have to worry that the area might drop. So generally when you take limits, weak limits